I guess people, huh?
Wait a minute or two. Okay, here we go.
There's not been two. Alright, so I'm happy to have Ibrahima from Johns Hopkins recently. Just started there, right? Yeah. Having a good time and surviving the Maryland weather over San Diego, where he's from originally. Going to tell us today about geometrizing superconformal field theories and ADS-CFT.
Okay, thank you for the invitation. The initial day that was chosen was tough because I had just moved to a university and many things to do. But I'm glad I finally able to come, and thank you very much for the invitation. And it's truly a pleasure to come here. Okay, so to start this discussion is a lot of what I will talk about is how do we do quantum field theory and how do we understand the space of quantum field theory, how do we classify them. So what we learn in school is that we construct quantum field theory by starting from some weakly Lagrangian point. You write down a Lagrangian, let's say the standard model, for example, and this QFT can flow can flow as you basically decrease the energy, or as it flows, the couplings basically change value and it can become strongly coupled. And the CFTs can land to some points in the deep IR, which we typically call some sort of a fixed point, right, where the couplings don't change anymore. And the picture that we're used to when we learn is that you start with some weakly coupled theory. So this is like you start with some sort of a Lagrangian over here. And then you let the theory run. It flows, and it can flow to some fixed points in the deep IR down here, and you can try to characterize these fixed points in terms of the Lagrangian data. Okay? This is how we learn how to do quantum field theory. And the fixed points that we have over here, which is at the end point of these flows, are typically what we call the CFT, or conformal field theory. They're scale invariant. So this is a picture that we learn. Write a Lagrangian and get fixed points and study fixed points. But in reality, what we're starting to find more and more, due to string theory, for example, is in fact, while you can write down a Lagrangian for some fixed points, CFT, in reality there are many more fixed points which are inherently strongly coupled, which basically lie somewhere deep over here. And along these fixed points, you can also have flows of all sorts of things between different theories, right? And all of these cases that you get, and any fixed point that you have at this, in this location, typically are non-Lagrangian. Meaning you do not have some UV point which flows to them. Okay. So if your interest is to understand QFTs in general and how they work and what are the basic rules for them, it is important to be able to have some description which also includes these in general, which is not heavily biased to only the ones from which you can write the Lagrangian. So some of the primary interests of this research, which has a large community now, is to understand how to study QFTs in general. And one thing that becomes immediately clear is if you want to have access to T's and put them in some sense in the same footing as the ones on top here, you need a new picture. You need a new picture and a new approach of quantum field theory. Okay. And one way to do this is to geometrize them. If you can give an independent and alternate definitions of CFTs, without having to refer to a Lagrangian, and then if you can also understand what the rules are for this alternate definition, on how to put them together, how to construct a general quantum field theory, then you would have been able to put all of these points in the same setting as the ones on top, and you could study QFTs in the space of QFTs in general.
It's not so much different than what you have in two-dimensional CFTs, where many Lagrangians are not known.
Yes. This is exactly the same. You think of the minimal models, for example.
Yeah.
Right? But we wish to now, where of course in 2D, if you can tell me the spectrum of operators and tell me the OPEs, then you would have defined the CFT. But of course, it's hard in high dimensions to figure it out. There is a rich bootstrap program that aims to do that, but also that's one approach of many. Today, the approach that I'm going to follow is one where you try to give some geometric definition of CFTs, and then try to understand how to classify them from this point of view. Thank you for this statement. So, the strategy in geometrizing this has gone through several names. One of the recent names that we call them is the Class S program, where the main idea is to consider 6D superconformal field theories and then you put these CFTs on some Riemann surface with a given genus and given number of punctures, and then you ask, when do you get a 4D CFT? So the benefit of this is that 6D CFTs are classified, are more or less classified. You can systematically go out there and write them and know what they are. Okay. 4D CFTs are harder. There isn't a good classification, and if you want to describe them in some systematic way, this is an approach which can be of great use. So the idea here is that if you take the 6D CFT and you put it on this surface, you can effectively define the 4D CFT as the 6D CFT plus whatever data that you get from the Riemann surface. Okay. So this is the big approach, which have gone under the name of Class S. When you take the 6D to 0 theory on some Riemann surface with a genus G. And the main proponent of this, of course, it started with the work of Gaiotto. And Gaiotto more Naisky around 09. Okay, so a couple of words on this. So what happens when you take this CFT on the Riemann surface, there are various nice properties that is geometrized that becomes trivial. Okay, so the class of theories studied here are going to be n equal to 2 4D superconformal field theories. And the value of having this is the Riemann surface gives you the Seiberg-Witten curve. Of the 4D theory. It allows you to obtain the spectrum of protected operators Moreover, you can understand the OPE for these guys, for example, you can understand the OPE by this guy by looking at the Gaiotto Tajikawa all-day duality, AGT. So AGT then allows you for the computation of these things.
So what's the duality supposed to be?
The duality between, so in this case, so what the duality is that if you want to study the OPEs over here, so I can say briefly about this, is you take this 6D and you consider this compactification here. So this surface has punctures. So you can, if you were to do it in reverse, where you'd say that I take this 4D theory and try to compute, let's say, the partition function on X4, and you consider the limit where the Riemann surface is large, then in that case, that surface is governed by a Liouville theory. Okay? And then the correlators for the 4D theory is going to be given by the Louisville theory on the surface. So this goes under the name of HET.
So it's a duality between a conformal field theory and Liouville theory, or what?
Yes,
So
the duality between a 4D CFT and a 2D Louisville theory, for example. So again, obtaining this data makes no reference of any Lagrangian. And of course, the list continues. There's many things that you learn by defining your CFTs in this way in studying. And one of the, also, for example, the moduli space of the Riemann surface gives you the conformal manifold, the conformal manifold of the CFT, which is a space of exactly marginal coupling. So it really moves away from the usual Lagrangian picture. Moreover, the typical CFT that you get in this case is going to be isolated, and it's going to be one of these classes, where in fact you can see this, the conformal field theory is a strongly coupled object. It's not weakly coupled.
Is that because of your starting point?
Hmm?
Is that because of your starting point?
It doesn't have to be because of the starting point. In principle, you can start with a Lagrangian theory and compactify it and get something that is strongly coupled. But in this case, the 6D CFT itself is a strongly coupled, isolated object.
That's what I meant.
Right.
That's why
Yeah.
I said because
That's not a reason. That's certainly an issue. But the 6D theory can also give you a Lagrangian theory. Right? For example, if you take the 6D on a torus, you get n equals to 4 Triangle theory. Right? So because the 6D is strongly coupled, doesn't necessarily mean tells you everything else is going to be strong. So let me put a little bit more meat in this discussion. So to just think about a simple example, the simplest object you can consider here is to take the 6D20 theory and put it on, compactify it on some sphere with 3 punctures. This is an object where there is no complex structure deformation. It's a three punctured sphere. So when you put this 2D CFTs on this surface, at each one of these points, at each one of these punctures, you need to give me some boundary condition. So the boundary condition will translate to adding global symmetries. It gives you some global symmetries. And if you wish, these addition of these boundary conditions that you add here actually are related here to the codimension 2 defects of the 6D. Of 6D theory. Okay? So an example, one simple example of a theory that you label this way is you can consider a compactification of 6D on this sphere of 3 punctures, such that the data associated to this puncture, you have something here which is a U1. You have one here which is some SUN. And then you get another one which is an SUN. So this theory is exactly equivalent to a hypermultiplet which transform under an SUN times SUN group, global symmetry. Where you have a U1 which acts here baryonically. So this is, for example, a simple example that you can study here. Right, so you take the 6D theory on a sphere, and you pick your boundary condition such that this is a U1 global symmetry, SUN times SUN. You understand this as a hypermultiplet. It's a hypermultiplet in 4D. And the boundary condition here are the ones that are consistent with the n equal to 2 supersymmetry. Okay? So if you have a hypermultiplet theory, you can, for example, take 2 hypermultiplets, and you can gauge the global symmetry here. And then when you gauge the global symmetry, here you get a NF equal to 2NC gauge theory. Okay? So geometrically, from this picture, this corresponds to taking two of these objects, and do what you should do if you have Riemann surfaces in three puncture spheres. You glue them along a puncture side. Okay? So when you glue, you're adding a tube by connecting these two. And the tube itself, if you think about the 60 to 0 theory on a tube, this manifestly gives you a vector multiplet in 4D. And this vector multiplet is exactly what you think of as the gauge field that you turn on in coupling these two. Okay? And you can, in principle, take a system with any global symmetry, and you can, for example, glue other punctures to get some higher genus surface. But then this object is going to be a more non-trivial 4D CFT, which is labeled by the genus and the leftover punctures. So in this way, this not just gives you a way of getting 4D series, but it also gives you intuitively what you think of how you should construct CFTs. Okay, so when we write, go ahead.
These operations commute. So if I'd started on a torus with two punctures in the same boundary conditions, I would get the same field?
Yes.
What is the interpretation of that statement?
So,
Torus.
yeah, so good. So what you're saying is that part of that is part of, the way you think of it is part of the duality group, right? So if you take these theories, for example, n equal to 2, you write down the Seiberg-Witten curve. You have various math parameters that you can dial around. So when you dial these math parameters, you can go to different weakly coupled regimes, for example. So if you think of it as just taking a torus with two punctures, right? And you go with this, you're starting one where the math parameters, where some math parameters are large and other are small. But you could have also gone by taking two of these trinions and then describe it first and then glue. So that's a limit where you've also taken a different limit. So let me be more precise in this. So if you think about, let's say, a sphere with 4 punctures, okay? So this is where you have these punctures. You have one moduli, which is, you can fix 3 of them. You have one left over, which is a modulus, which you can move around, for example. Okay? So you can ask, what is that operation of moving things around? So if I take the 60 theory and just put it here, it is some strongly coupled thing. But let's say I consider a limit where I write this in this way, where I put the 2 punctures here, and I put another 2 punctures here. So in this limit, I've dialed my parameter associated to such that I get this very long tube. So this very long tube is effectively going to be a vector multiple. Right. So this is some weakly coupled limit for that vector multiple. So more properly, you can draw this like this. Where you have the 2 punctures here, and then you have the 2 punctures there. Okay? So you can see topologically these are equivalent, right? But there is a parameter that I'm allowed to dial, which you think of as a gauge couple. So the idea now is if you want to have a more generic picture of describing your CFTs and able to have some kind of democratic way of accessing everything, this might be an approach you should follow. Think about the 60 theories that you have and put them on the Riemann surface. So every time you take a 60 theory on a Riemann surface, it defines a family of theories. And each family of theory is given by the Riemann surface and the data that you give at a single puncture. Okay? Then if you want to classify them in a way that you can start building theories in this way, in almost a Lagrangian sense, then the question you're asking is, what are all possible? Question now you would like to have is, what are all possible spheres with three punctures, right? So the idea is if you understand the collection of these objects, then by using the usual geometric building, right, then you can construct any arbitrary quantum field theory and CFT as you want. In reality, what you want is you want to know what are all possible three-punctured spheres, and also what are all possible tubes that you can have. Like the tubes are the gluing blocks.
So this would presumably give you all the theories in class S. But there could be other 4D SCFTs that just don't arise.
Yes, there could be other 4D CFTs that just don't arise from this way, but they may arise by taking some of these things, doing some sort of deformation, and then flowing to those. Okay, so like for example, you might think Archer Douglas theories may not arise in this way, but now using the equivalent n equal to 1 blocks, you can actually construct Lagrangian things that look. You can take these n equal to 1 blocks as a Lagrangian sense. You glue them in some way, and then you can argue that when they flow to one of these theories.
I have another basic question. So in the example with the mass deformations, why is that a CFT? Are the mass parameters corresponding to marginal operators?
Yeah. So this is just a language in this. In fact, the parameter is really, you take the ratio of the positions of the punctures, right? So this gives you the mass parameters, and those are actually the moduli of the surface puncture.
And do you know whether all n equal to 4D CFTs are class S?
So
I thought that was originally the statement, but then.
No, it's not quite true, right? So certainly, if you can construct a Seiberg-Witten curve, you can probably put it in this form, okay? But that's not obviously true. Also, another one that are clearly not included in this, if you have orbitals of n equal to 4, and n equal to 2 orbitals of n equal to 4, they're not immediately part of class S, for example. Good. So the idea is, so you want to get all possible CFTs. Now instead of starting with trying to build Lagrangians and then flowing, you have a more general object which in appropriate limit reduces to a Lagrangian. Okay. So if you know all the collection of all of these three-punctured spheres, right, that you can have, and the collection of all possible tubes, then in principle you can build much more complex set of quantum field theories.